Alright, hello friends, Hi-Fri here. I got a special one for you today. So kind of teased it, I don't know, a couple of weeks ago in one of my community posts. But today we are going to look at not a prototype of the Celeste Phoenix-call IEM. This is a prototype that they sent to me for evaluation. This is not a final unit, so just keep that in mind. The internals are much different because it's a prototype. It's very raw. The shell's raw. It's not anything like the final version. The tuning has changed since this prototype, so just keep that in mind. But that's not really the whole point of this video. I will show off the drivers, but more so I wanted to show you some graphs over here and kind of explain why I feel that these flat panel drivers have a lot of potential. I don't think they've quite reached the potential of Sonyan EST. So for example, I have a Sonyan EST unit here. It's very well used, very well loved. It's been in many prototypes of mine. I have another one here somewhere. I got a 10BA 4 EST prototype that's been sitting here for much too long. But anyway, so I wanted to kind of talk about how these flat panel drivers are kind of like a poor man's EST. They have a lot of potential, in my opinion, but I think it might take another revision until we really get to that point where we start to see the same performance as like an EST unit. And then I also wanted to compare it to some options that we do have today that are, for instance, this like I have here a 5mm beryllium dome tweeter. This does not do anything other than highs. That's all this does. So this only does treble. But I wanted to kind of talk about it in my personal experience with the different technologies for treble. So before we get into that, I'll just pull some of this stuff off to the side, and we'll start with, we'll start with this. So this is the Rinko driver. Okay, this I believe the driver was made by QDC. You can see it's a combination driver. So there's a 10mm like a biofiber, I believe. It's really thin. It's like a TWS style driver. But so there was this that came out not too long ago, and it has a 6mm flat panel driver on top that QDC created, and then it has the 10mm dynamic, underneath it. So this is one of the iterations of these drivers. Now this uses a strictly like a PET membrane for the diaphragm. It does not use any kind of metallized coating or any special coatings, nothing like that. Sorry, I need to turn this off real quick. So anyway, it doesn't use any special coatings or anything like that. It's just a typical diaphragm, except it's completely flat and has a voice coil directly attached. And then also there's some dampening. So you see they have some, they have some dampening on the front there. That middle hole, that's where the treble comes out of. And then the surrounding holes, that's where the mids and the bass come from. And part of this design is kind of cool because in a speaker, most of your mid highs come from the center dome. So the way this is stacked on top of each other, this actually blocks the dome. So the residual sound you get from this surrounding area here is more of the mids and the bass. So it kind of lends itself well to having this tweeter on top. And then also there's a little, focus. There is a crossover unit right there. So it's just a small, tiny little capacitor. That's all it is, just an itty bitty capacitor that they used, and that is what filters the mids and the bass from the flat panel. So that came not first. Actually, I'll show you what came first. All right, so while my soldering iron's heating up, so this is what pretty much came first, except a different iteration of this. So this is the MStat, or the magnetostatic driver. This is the same driver that we saw in the Shure tape, the Shure, what is it, shower, whatever you call it. But anyway, there's a few of their IEMs that had this driver, but this is the magnetostatic driver, and the principle that this functions off of is completely different to any of these. Well, especially those, but it's completely different to these flat panel drivers, including this one. So completely different principle. It's kind of hard to explain, but you have moving coils in these drivers here, these flat panel drivers. There is no moving coil in this driver here. There's a moving plate. The coils are standard, so they're like stators, basically. They stay in position. They don't move at all. You have two permanent magnets, and then you have two field coils, and then there's a plate in the middle, and that the two field coils, with the help of the magnets, move this diaphragm in and out. And I'm currently warming up my soldering iron because I want to show you the graph for this as well, because I have a bunch of these. But anyway, so this is what we saw in the last like year or two ago. It was in the ZST, or what is it, the Crin ZEX. Sorry, it was in the ZEX, the ZEX Pro, and then eventually the Crin, the CRN. But this is like a super tweeter, as they would call it, or like a magnetostatic tweeter. So essentially, it only does highs. It doesn't do anything else. This is a specially designed one from KZ, from their manufacturer. This is like a second gen. So originally what we saw, and I have no idea what IMs it was in. I'm actually getting ready to buy a couple just because I'm curious. I need to satisfy that curiosity. But the first ones that I believe were created they're like 12 millimeter. Oh, Jesus Christ. Focus, you fuck. So they were 12 millimeter, and they were magnetostat drivers, except they use a metal plate, but the metal plate is affixed on top of a crystal. So it's almost like a piezo effect, but different. And it still has the stationary coil, except instead of two, there's only, I believe, one stationary coil and one permanent magnet on the edge. And the metal plate is on the crystal, and I think the crystal helps it vibrate, and maybe it uses less magnetics. These have much stronger magnetics in them, and two opposing coils instead of just one. So I don't know how much better these are in comparison to like the 12 millimeter version. I mean, 12 millimeters is big. 12 millimeters is like that big. So, but anyway, so that is your magnetostatic driver. So that's like the first iteration of like a flat driver. And this is the one that we had for a very, very long time. And then just recently we started moving on to these flat panel drivers, which are kind of like a cross between a planar and a dynamic. That's why some companies, semantics, like they're not really sure what to call it. So some call it planar. Canera, they call it like their flat panel driver, which I think is more appropriate because it's not really planar, not in the truest sense of the word, but it still has planar qualities to it, if that makes any sense. But anyway, so today I wanted to show you a little bit of what has gone into the Phoenix-call and a couple of Canera's new IEMs. I have another prototype here. I can't really tell you what prototype it is, but there's another prototype that I'm using. And anyway, so what we have, or what this IEM consists of, are two flat panel drivers. Now this is per earphone. I don't have the other one. I tore the other one apart. But there's 2 flat panel drivers per earphone. Then we have 2 customized balanced armatures. Now, I believe these are both made by Belzing. So we have one for the mids and one for the highs. And then we also have a dynamic driver here. It is I believe it's a 6.9 millimeter. They could correct me. It might be 7 millimeters. I mean, they might say it's 7. But this is a driver that Canera likes to use in a lot of their IMs. A lot. They've used it in their iDone. They've used it in Nana, I believe. So it's a driver that's fairly universal, and it's a very good driver. It's a very excellent driver. It's very good. So I have no complaints with the driver whatsoever. It's pretty versatile. It can be tuned in different ways. And they have their own tuning methods. The way they like to tune their IMs are completely different from the way I tune my IMs. You know, some stuff we agree on, some stuff we don't. But anyway, for the most part, this is what is inside the Phoenix-call. Now, it's a completely 3D printed chassis of their own design, and it has this interesting shape. Now, it does feel good in the ear. I'm not going to comment on any sound impressions whatsoever. I'm not going to give you guys any sound impressions. That's not what this video is for. This is a prototype. I don't have the full version. Hi-Fi Go offered me the retail version, but I told them I was too busy, and I just don't have the time to review it. But anyway, and I mean, I already have the prototype. I already know pretty much all there is to know about it. So anyway, that being said, so I will crack the back open real quick, and I'll show you guys the layout of the drivers. We have 4 ports on the nozzle here. Now the retail price is 129 bucks, which I think is actually a really good deal for what you're getting technology-wise and R&D and all that. I think a lot of work went into it. Like I said, I'm not going to comment on the sound or anything like that, but for everything that's involved with the IM, I mean, I think you're honestly getting a pretty good deal. The build quality is really nice. But yeah, so you have 4 nozzles here, and I'll explain each nozzle to you. So we have one for treble, one for mids, one for bass or the dynamic driver, and then one for the 2 FPD or flat panel drivers. Now, the distance between the drivers to the ear are different. One of them's over here, one of them's a little bit closer. I mean, does that make a real big difference? I don't think so. But yeah, essentially 2 of them double the output. They are pretty sensitive drivers, so you're really getting a lot of treble output with those drivers. But yeah, so essentially 2 flat panel drivers, 2 balanced armatures, and 1 dynamic driver. And I mean, because of the shape of the drivers, this really is the best, most compact shape you can have in this IM. But anyway, at the end of the video, I will tear this apart. But yeah, so I just wanted to show off these drivers to you real quick. Now, I'm not going to take the what do you call it, the Rinko driver apart. I'm going to save this because I have plans for these drivers. This is the only pair I have, and the Rinko's like $100, so I'm not going to destroy them. If anything, one day I might try to make the QDC Leaf, I think it's called, because I have the 2389s, so I could just add a 2389 and wire up this driver and try to make my own QDC Leaf. But anyways, I will show you the insides of the Canera FPD or flat panel drivers, and I'll just give you a little close-up of the driver itself. So the hole is off axis, and I don't know if having the hole in the center, if that would make any difference with the sound or the tuning, if it would make it any better. I haven't really experimented with these drivers at all, but you'll see that you have the 2 input terminals and these little leads that are soldered on, because it really is a small, tiny driver. I mean, it's only like 1 millimeter thick, And so you have a little dust cover or a little mesh on the top that's just, in my thoughts, to keep dust out. It could be for tuning purposes, but I don't really think so. I think it's more just to keep dust and debris out, keep the driver clean. And then you have this little flex PCB ribbon. Now that's just to carry the signal across to the input side, where the two terminals go into the driver itself. Okay, and yeah, so that is the flat panel driver, and it, I mean, if you look at it head to head against the QDC driver, you know, they're about the same size, so not much different there. And give me 1 second, I'll be right back, because I just need to wire up this this driver real quick, this MSTAT. Alright, ladies and gentlemen, I am done graphing the device. Man, that is really blown out. Sorry, guys. So anyway, so I have my pre-disassembled unit here, and we will take this apart. I think next video I'm going to switch back to my old camera, because this Google Pixel camera sucks. Either that or I'm going to have to try working with Gcam, because this is just not working out for me. So we have this little lid on top. Alright, I'll show you the diaphragm in a second. But this is the magnet structure. So we have two magnets of opposing polarities. So one is north and one is south. And they are touching, which I don't think is best for the magnetic flux. I think in a future revision, they should have a gap between the two magnets. You know, maybe have the north be like half the size of this one and leave more of a gap. Because a lot of people don't realize, but magnets, their poles stretch out from the magnet, and they, you know, they travel around. But anyway, the greatest point of intensity as far as like magnetic pull goes, or magnetic force, is not always right next to the magnet. It's usually you know, a little distance away, and especially when you use like metal, or ferrous metal. That ferrous metal essentially completes the field or extends the field and makes the field bigger or stronger, has a greater area of effect. So anyway, having these two magnets so close together, I think could possibly have a diminished effect. But it also depends on the placement of the voice coil. There's a certain criticality where you need to have the voice coil to achieve maximum flux between the electromagnet and the two stationary or permanent magnets. So anyway, so this is a magnet structure. Like I said, it's two opposing magnets, two different polarities, and that's pretty much it. And it's just in a little dish, little wafer. You do have, and I hope you can see it, there is a little ring inside. I don't know if I can pull it out. There is a little tin or copper ring, and that is just for the voice coil, or the diaphragm, to sit on top of. So here's the cap. I'm just gonna pull the cap away. All right. Then I'll show you the underside of the diaphragm first. All right, so here is the underside of the diaphragm, and you can see it is a like metallic coated diaphragm. So of course that aids in the rigidity and probably helps a little bit with the speed of the driver, but then again, having that hole off axis and not on center, I don't know if that benefits the sound at all. I would imagine having it on center would help benefit the driver a little bit, but I don't know. Who knows? But anyway, yeah, so there it is. And it's just a precise wound voice coil on this little teeny sheet of Mylar or PET or some sort of plastic. And this is the side that you see. So this is the side that communicates the sound. Is that side there. And you can see, judging by the metal area and the little disc here, it's drawing its sound from right at the edge of the metal disc. So, but anyway, yeah. So that is the technology that we're seeing with the new FPD drivers or flat panel drivers. And like I showed you before, so this is a 5mm beryllium dome. And just to show you the breakdown of that, so this would be like your traditional driver. So there's the dome, you have a little teeny bit of a surround ring, and then you have this huge beefy voice coil. Okay. And because the driver is metal, there we go. It's very stiff. Now it's still coated. It's got some sort of plastic coating or whatever, but because it's metal coated, it's extremely stiff. But these make great tweeters. They really do. But yeah, so this is like the traditional technology would be this like 5mm beryllium driver. That would be your traditional type of tweeter, and then your flat panel tweeter, and then same thing with this driver. You know, you get highs out of it, but this, you know, is your full range dynamic driver. Same principle, but the coil is perpendicular. It's not flat and parallel with the diaphragm. So, and then I've already taken these apart. I guess I could show you. Well, I've already taken these apart in another video. You guys can look that up if you want, but this is the MStat. So, anyway, so let's look at some graphs real quick, and then we'll take apart the Phoenix-call. All right, so this is the magnetostat driver that I just measured, and this is actually a very good response. I'm surprised I haven't measured them sooner. I've never really measured them before, and I don't know why. Maybe because I just thought they weren't a viable driver, but this is actually kind of encouraging. I think I might actually experiment with this driver in one of my next IMs. But anyway, so this is the profile of the driver. It's just, you know, I think the lowest point that's not getting too crazy as far as the amount of dB roll off, probably be around, what is that, 8? Yeah, like 8 kilohertz would probably be the lowest point without like a crazy amount of roll off, you know, where it's still in the audible range. But then you get this huge peak here, and that is at 12.5K. That's where the tallest peak is. So that's crazy, because that's like pure treble. I mean, that's just pure treble energy. And it extends all the way out. So the next second peak is 14.4, which is awesome. And then we have a third peak here, which is a little bit lower at 16.1. So, I mean, that's a very capable driver of treble. And got to remember, this is the MStat. So this is what KZ was using a year or two ago. Now, I'll get into the main problems of these drivers in just a second when we tear apart the housing. I'll kind of talk about the whole reason why these haven't been used more widely, and why they're sort of relegated to being a niche driver technology, but we'll get into that in a minute. So anyway, so that's the MStat. This is the Rinko driver, okay? So we got a little bit of funny business going on, but realistically, you're not going to hear any of that. The majority of what you're going to hear is up in this range here. So we have a peak at 7K, which you would have to kind of plan your tuning around this area here. Maybe you'd have to have a balanced armature that has a dip in this area, this location, or depending on the proximity of this driver to the nozzle, maybe it'll work out where it'll fill in a valley. It all just depends with experimentation and whatnot, and also you can use dampening to kind of help. But I'm not a big fan of these huge peaks. You can see when we go back to the magnetostat driver, there's a lot more uniformity, or at least there's not as much variance in the range throughout the spectrum. This could easily be dampened, or this could easily be added on to other drivers, because a lot of balanced armatures kind of taper off around this area. So this would be a perfect driver to kind of fill in after the fact. But you can see here with the Rinko, it's just a kind of just a giant spike and then just goes back down. So you're really not getting a good amount of bandwidth. So this driver kind of lacks bandwidth. It has the gain, and it has treble. I mean, that's 13.8K is where that peak is, 13.7. So it's definitely upper end of the treble region, but I mean, it drops off significantly on either end, relatively close by. So not a great driver for treble. Maybe if it were reworked or tuned a little differently. Obviously, putting it in a shell with a nozzle and stuff where the frequencies kind of bounce around a little bit, it changes things. Everything changes. This is all just in free air using the coupler attachment. So you just got to keep that in mind. These graphs look really weird to the untrained eye if you don't know what you're looking at. But if you're someone like me who's familiar with your setup and you're familiar with the graphs that you take, then you'll kind of understand what's going on here. But anyway, yeah. So not great, good, but not great. Compare it again to MStat one more time. You can see that there's a little bit more bandwidth in the MStat, and the coverage is a little more even. Then here we have the Canera, the flat panel driver. Now things have kind of changed a little bit in this case. Still a really good amount of coverage, but it's shifted much lower. So again, we'd have to choose our balanced armature carefully and make sure that it starts losing energy at 7K. Now we could probably cross this over a little bit, but the problem is with impedances this high, you tend to lose a lot of gain, so you can't really apply too much of a frequency divider on this driver. Of course, you can cut a little bit of this back, but you don't want to cut too hard on it, because this driver will become a like a straight resistor instead of a impedance. So it'll be like a straight resistance load. But anyway, so we actually have a pretty good curve here. There's a lot of energy from 7.5, 7.6 to like bang on 10K. But after that, it kind of goes down, and it does travel down a few dB, but the valley is not that deep, and it regains energy and a pretty decent amount at 15K. So this amount of coverage here, that's really not bad at all. That's very manageable. So I definitely see why they've seen potential in this driver. Here's the same driver with some added dampening, some mesh. So this is one 350 mesh on the outlet. And you can see it's kind of starting to look more like the MStat driver, kind of cutting into it a little bit. So Dampening probably isn't the best move for this driver. Might want to apply a little bit of dampening just to get rid of any kind of issues with timbre or whatever. But you probably don't want to apply too much because you'll start cutting away at the bandwidth and the frequency response. And then here's the mesh times 3. Now this kind of shows the opposite effect, where if you clamp down even harder on the dampening, you might be able to cut these spikes down more, or these like little resonance peaks. So yeah, so it's just R&D. I mean, that's literally what R&D is research and development. You try something, does it work? Does it not work? Okay, you iterate on that, you keep going, and you eventually find something you like. So that is the Canera flat panel driver, and again, we'll compare to like MStat. Okay, so you can see much more energy. So first off, they're much easier to drive. Okay, so there's the Canera driver, huge amount more gain. But the frequency response is kind of shifted a little bit. So we have the majority of the energy here, which is something that you'd have to kind of battle with a little bit when you are tuning the driver. Then we have the 5mm beryllium driver. Now these are kind of weird because I bought a few of them and every single one of them graphed differently. I took the two most consistent here to show you guys. So there's one. All right, you can see there's a lot of energy kind of focused in one location, kind of tapers off around 11, almost 12 kilohertz, but the majority of the energy is around probably right at close to 11. Yeah, probably like right on 11 almost. And then we have another peak here at 9. But the coverage is pretty smooth. There's definitely roll off. It doesn't extend too cleanly, but the energy is there and the coverage is pretty even. So this would be an easy driver to tune with other drivers. And dynamic drivers are very receptive towards adding frequency dividers and such. They don't tend to turn into a resistance. They tend to remain an impedance. So here is just a brief illustration of kind of the extension you can achieve with a traditional electrostatic driver, or not electrostatic, not true electrostatic, but the Sonian drivers. And this is one of the reasons why Sonian drivers are as expensive as they are, because they really are the closest we've gotten to a super tweeter. They really are the superior form of high frequency technology, but they're so damn expensive. That is what justifies these companies looking into cheaper alternatives, and that's literally exactly what I've been doing for the last like 2 years. I've been looking at other means of technology to compete with these Sonian electrostatic or electret type technology, just because it really is awesome. So this is a DIY IM that I made, kind of based off the EJ07, kind of based off of the variations, not in tuning, because this is when I was like first learning. I've learned a lot since then, but this is when I was first learning. So it's one dynamic, two balanced armatures, the 2389D, and then two Sonian drivers. But you can see here the extension is just off the charts, insane. We do have a peak here right at 8K. Now that could be a coupler peak, but I don't know. I'm probably more inclined to think that that's real, just because of the shape of it, and the fact that it's regaining energy after this dip here. But you could see afterwards the extension is just insane. We have another dip here around 11 kilohertz, but then it regains energy at 13, goes all the way 14, 15, 16, starts dipping at 16.1, 16.2, dips down a little bit at 17, regains energy at 18.1, goes to 19, 19.2, and then falls off. That is insane. Okay, now you can't really trust these couplers after 8 kilohertz, but trust me when I say that my ears have heard this IM. I tuned it with my own ears, and yes, the treble extension is insane on this IM. I intentionally tuned it to be that way, and I kind of discovered the magic between or behind the electrostat driver, and yeah, so that's basically what those drivers are capable of, and I mean that's just some people would die for extension like that. But anyway, so overall, not the best looking graph, but as far as the extension goes, it just goes and goes and goes. Now here is an example of what the raw Sonian electrostat driver looks like, and it's a completely different beast. You see these huge dips. Obviously, when you add other drivers into the mix, it kind of fills it in. So we have a peak here, we have a secondary peak, and then we have a third peak here. This would also we gain energy the higher we get in frequency, which is a really good sign. A lot of people don't look at the way the peaks shift. So if you have a driver that has a peak that or a slope that goes like this, so it goes like largest peak and then it goes down, secondary peak and goes down. When you go to tune that driver with other drivers, that primary peak is still going to stay in that area. That's where the most energy is going to be. But you see how this driver has an incline as it gets towards the higher frequencies. That means you're still going to maintain the majority of the energy from this driver in these outer frequencies. Also, because it's gaining in amplitude, I believe, don't quote me on this because I may be wrong, I haven't looked at the impedance curve, but I believe that could mean that the impedance is less as you get into these higher frequencies, which could be because of the transformer that they hooked up to it, because they do all have these little transformers on them. But that's another reason why the driver is so expensive. It's literally tuned to be a super driver, and you can see yet again the extension goes off the charts. It does lose some energy from its highest peak, about, what is that, 108, 102, 94. So it's like 14 dB. But I mean, that's still a lot of energy, 94 dB. At because I measure all my drivers at the same gain or whatever, same output. So I mean, 94 dB. That's pretty damn good. Even though the driver itself really isn't that sensitive in all reality. But yeah, I mean, so anyway, so that is the Sonian driver, and you can compare that to the MStat. You see how narrow that is. So you're looking at that and you're like, holy crap, that's nothing compared to the MStat. And then we have the Rinko, and that's all funny. And then we have the Canary driver, which is not bad. But like I said, the major peak is in this area, so you're going to be battling with this area here, which means your other drivers are going to have to start tapering off in this area for it to properly transition over to this flat panel driver. And then the beryllium driver, and then again the Sonian EST driver. And then here's with a little bit of dampening applied. So this is the black dampener. This is a 330 value. And then this is a 600 value. And this is using, it says 9.5 millimeter tube. I have no idea if that's true. If so, that's wicked long. That's way too long. But anyway, so that's, you can add dampening to the EST. Do I recommend it? No. Personally, I just use a slightly more narrow tube, and I think that works fine instead of using dampening on the EST. But what do I know? I'm still a DIY guy, and I'm still learning just like the rest of you guys. But anyway, that's a little overview of all the different driver technologies that I've come across and their various, um, frequency responses and whatnot. So anyway, I just found it kind of interesting and thought maybe you guys would get a kick out of it too. All right, so before my phone overheats, as promised, here is the Phoenix-call prototype. And just be warned, it is a little messy. It is a prototype. It's not a final revision. So it's going to be a little messy inside. Alright. Plus I made some changes and stuff, played with it a little bit. So we have our, where's it at? So first off, everything in here is hand soldered, no PCBs. But you can see we have, if I move some of this stuff out of the way. So we have one of the flat panel drivers in the rear there. We have our dynamic driver here on top. This is the much loved driver that Canary uses in a lot of their IMs, like the iDone Golden. I believe the Nana uses the same driver. You'd have to confirm with Canara. And then, sorry, there's glue and stuff, so it's hard to move the wires around. But then there is the second flat panel driver, so the two of them on either side. Then we have our two balanced armatures, or mids and highs, and then a little relief vent here. This is just for the dynamic driver. Well, anyway, but yeah, so that's for the dynamic driver. And then we have our frequency divider circuit with all kinds of stuff in it, and that's why it looks messy, just because it's a prototype. So this is very common in the world of prototypes. You can ask anybody, and they'll tell you, yep, that's what my prototype looks like. So anyway, guys, I hope you enjoyed this video. I know it was kind of a crazy misadventure, but I don't know, maybe I'll show you guys some other stuff later. But now I'm actually kind of excited to dive back into these magnetostat drivers. So yeah, so real quick, just to touch on what I was saying earlier. The main disadvantage to all these drivers, and the reason why none of them have really superseded the electrostat or electric drivers from Sonian, is because of timbre. Okay, it's because of the sound quality, the resolution, just how wispy and everything, and detailed the electric or the electrostatic drivers can be. All of these flat drivers, to some extent, have some sort of metallic timbre or sharp timbre or grainy timbre, or all of them. I mean, even the beryllium, the 5mm beryllium domes that I have some weird issues with timbre. But like the extension's good, frequency response is good, but yeah, timbre is the big issue, and that's what these companies are working with. But I'm just excited. I hope that more companies go forward and keep refining this technology, because this is much cheaper to produce than these. These are very expensive to produce because of the wound transformer and the delicate nature of the electrostatic or the electric unit. So anyway, these are much more affordable for manufacturers to produce, which means that they are much more affordable for you to enjoy. That's why your tribrid are so expensive. That's why you won't see a tribrid IM below $400, $500. I mean, the absolute cheapest one you can get right now is like $450, and that is a 1DD. I think it's like 8BA and 2 EST, but there's like the graph looks bad. There's no history behind it, no reviews, no nothing. It's just really questionable. But then you have companies like GS Audio where they have a couple affordable tribrids, you know, that are like in the $500 range, a little bit less than $500 for the 122. But that's the majority of what you see is a 122. So 1 DD, two balanced armatures, and two ESTs. That's like the the meat and potatoes of the IEM world or the tribrid world is one dynamic, two BA, two EST, just because it's the most affordable, it's the most well-rounded, and it's like the least amount of drivers that you can use to achieve the greatest amount of sound. Of course, you can go up from that point. You can get into stuff like this where you have 10 balanced armatures and 4 electrostatic drivers. You know, or you could do more or less even. You can do whatever, you know. But anyway, you know, this technology is a lot more affordable. So there's a lot of incentive for companies to use it. But the problem is that even though it's more affordable, there's still a lot of R&D cost that goes into it, which makes it not prohibitively expensive, but still makes it expensive, you know. It would probably be cheaper just to clone these than to get into this, but, you know, who knows. Anyway, I'm rambling on. I'll catch you guys later. Hope you enjoyed the video. Peace.